Hello and welcome to this video lecture on LC3 instructions. We will be covering the following 8 instructions in this lecture. I will describe what each instruction does and also how it does it. We will also look at the LC3 state diagram for each instruction and go through it step by step to figure out exactly what happens when a program encounters the instruction. We will now cover the jump and return from subroutine LC3 instructions, which have the opcode 1100. When a program encounters a jump instruction, it unconditionally jumps to the location specified by the contents of the base register in bits 8 through 6. The operation that occurs is that the PC is set to the base register. The jump instruction can be used to overcome the limitations of a conditional branch instruction. Recall that the conditional branch instruction can only access instructions that are 256 locations ahead of the branch or 255 locations before the branch. Since registers contain 16 bits, i.e. the full address space of memory, the jump instruction has no limitation on where the next instruction to be executed must reside. The return from subroutine instruction is a special case of the jump instruction. When the return instruction is encountered, the program counter is loaded with the contents of R7, which contains the linkage back to the instruction that follows the initial subroutine call instruction. Remember that the return instruction is simply a JMP R7 instruction. And here we see that in the LC3 state diagram there is only one micro instruction associated with the jump instruction, and that is to set the PC to the base register. The next LC3 instruction we will look at is the jump to subroutine instruction, which has the opcode 0100. Here's what the jump to subroutine instruction does. First, the incremented PC is saved in R7. This is the linkage back to the calling routine. Next, the PC is loaded with the address of the first instruction of the subroutine, causing an unconditional jump to that address. In the case of the JSR instruction, i.e. when bit 11 is set to 1, the address is computed by sign extending bits 10 through 0 and adding this value to the incremented PC. In the case of the JSRR instruction, i.e. when bit 11 is set to 0, the address of the subroutine is obtained from the base register. Once again, note that the JSRR instruction has access to the full address space of memory since registers contain 16 bits. The JSR instruction, on the other hand, has only an 11-bit PC offset to work with. In the LC3 state diagram, the first micro instruction for the JSR instruction is to load the PC with R7. In order to differentiate between the JSR and JSRR instruction, bit 11 of the instruction is checked. If bit 11 is set to 1, we have a JSR instruction, and the 11-bit offset in bits 10 through 0 is sign extended to 16 bits. The result is added to the incremented PC and loaded into the PC. Conversely, if bit 11 is set to 0, we have a JSRR instruction, and as was the case with the JMP instruction, the PC is simply loaded with the base register. Next up is the store LC3 instruction, which has the opcode 0011. When the store instruction is encountered in a program, the contents of the register specified by SR are stored in the memory location, whose address is computed as follows. Sign extend bits 8 through 0 to 16 bits in length, and add the resulting value to the incremented PC. Hence, the store instruction is PC relative, just like the load instruction. Note that the address specified by the PC offset can only be plus 256 or minus 255 locations of the store instruction, because that is the range of a 9-bit 2's complement binary number. Looking at the LC3 state diagram, we can see that there are multiple micro instructions associated with the store instruction. First, the incremented PC is added to the sign extended value contained in bits 8 through 0 of the IR, and the result is loaded into the MAR. Next, the contents of the source register are loaded into the MDR. Lastly, the contents of the MDR are loaded into the memory location pointed at by the MAR. Moving on, we have the store indirect LC3 instruction, which has the opcode 1011. When the store indirect instruction comes up, the contents of the register specified by the SR are stored in the memory location whose address is obtained as follows. Sign extend bits 8 through 0 to 16 bits in length and add the resulting value to the incremented PC. Whatever is in memory at this address is the address of the location to which the contents of SR are stored. This may seem a bit confusing at first, but looking at the pseudocode for the operation should help you understand what's going on. The store indirect instruction specifies the indirect addressing mode, just like the LDI instruction. The address is formed in exactly the same way as with the load or store instruction. However, instead of this address being the address of the operand to be loaded or stored, it contains the address of the operand to be loaded or stored. This allows the STI instruction to access the full address space of memory, as was the case with the jump instruction. The LC3 state diagram shows us 5 micro instructions for the store indirect instruction. First, the incremented PC is added to the sign extended value contained in bits 8 through 0 of the IR, and the result is loaded into the MAR. Second, the memory is read and the contents of the MAR are loaded into the MDR. Third, since the contents of the MAR are not the operand, but the address of the operand, the MDR is loaded into the MAR. In step 4, the contents of the source register are loaded into the MDR. Lastly, the contents of the MDR are loaded into the memory location pointed at by the MAR, completing the store indirect instruction. Another store instruction in the LC3 is the store base plus offset instruction. The opcode for this instruction is 0111. Similarly to the LDR instruction, the SDR instruction specifies the base plus offset addressing mode. The contents of the register specified by SR are stored in the memory location whose address is calculated as follows. Sign extend bits 5 through 0 to 16 bits in length and add this value to the contents of the register specified by bits 8 through 6, which is the base register. Note that the base plus offset addressing mode also allows the addressing operand to be anywhere in the computer's memory. There are 3 micro instructions associated with the store base plus offset instruction. First, the MAR is loaded with the base plus 6-bit offset. The next 2 micro instructions are identical to the second and third micro instructions for the ST instruction. They are as follows. Load the MDR with the source register, and finally load the contents of the MDR into the memory location pointed at by the MAR. The last instruction we will look at in this video lecture is the trap instruction, which has the opcode 1111. The trap instruction is useful for getting data into and out of the computer. Essentially, it changes the PC to a memory address that is part of the operating system, so that the operating system will perform some task on behalf of the program. In technical terms, we say that the trap instruction invokes an operating system service call. Bits 7 through 0 of the trap instruction form the trap vector, which identifies which service call the program wants the operating system to perform. Once the operating system has performed the service call, the PC is set to the address of the instruction directly after the trap instruction, and the program continues executing as normal. Let's look at how the trap instruction achieves all this. First, R7 is loaded with the incremented PC, which allows a return to the instruction following the trap instruction in the original program. Next, the PC is loaded with the starting address of the system call specified by trap vector 8. The starting address is contained in the memory location whose address is obtained by 0 extending trap vector 8 to 16 bits in length. Finally, let's look at this LC3 state diagram and examine the micro instructions that correspond to the trap instruction. In step 1, the MAR is loaded with the 0 extended 8-bit trap vector, which is in bits 7 through 0 of the IR. Step 2, the memory is read and the contents of the MAR are loaded into the MDR. Additionally, R7 is loaded with the incremented PC, which enables the return from the service call. Lastly, the contents of the MDR are loaded into the PC, completing the instruction cycle. This concludes this video lecture on LC3 instructions. You should hopefully have a more in-depth understanding of the LC3 instructions and what goes on behind each instruction. Thanks for watching.